Okay, so x plus 3 for the domain of x greater than 1. So all the x values that will be larger than 1 will be using that function x plus 3 on that. The second piece says x minus 2 for all x values that are equal to or less than 1. So basically the idea is if we are looking on our number line, this was your x-axis, then all the x values that are greater than 1, you are going to be using x plus 3 as your function. So all those y values will be calculated based on that. If you are looking at including 1 and anything that is to the left of it, so this is for the x less than equal to 1, you're using the function x minus 2. So that's what we'll be using to calculate the y values for that second piece, right? So the idea is, of course, choosing the right graph, because we need to know what those graphs will look like on each part of the domain, and then of course selecting our domain and range. So what do you think our graph should be for this one? X plus 3 for all the values x greater than 1, and x minus 2 for x equal to and less than. So let's look at option A. How do you know if the graph we're looking at is the right graph? How would you decide that? Say that again.
So they're shared.
Okay,
They're equal. I'm talking about.
so you're looking at the full circle and the empty circle to try and see if that would be right. What else?
Like with the -2, say x is less than or equal to 1.
Because you're equaling 1 in that definition. Okay. So looking at those circles, is it the open circle, closed circle? What else do we need to verify that we are looking at? Yeah, you need to test for numbers because you want to make sure that all the x greater than 1 values are using the right function, right? They are all going to be x plus 3. So remember, we had created a table for this purpose. So we had done, let's say x and y, and this can be for that first piece for which x was greater than 1. But remember, I had told you we needed to know if the two pieces would be touching or not touching. So we needed to make sure to include that 1, even though, they're telling us x is greater than 1, we still need to know what the behavior would be. So 1 plus 3 would of course give us 4. So you can see at the value of 1, 2, 3, 4, you should be at 4, and we do have an open circle there. So that looks good. If you did 2, of course, 2 plus 3 would be 5. So at 2, we should be at 5. So obviously that graph, that line is looking fine. Now let's do the other one. This one will be for -2. And remember here we were using x is less than equal to 1. So again, you would start with 1. 1 minus 2 would give us -1. Then you're going less than. So that would be 0 minus 2 is -2. You can do -1, which would be what? -3. So you want to verify you're hitting those points. So again, at +1, we should be at -1, which is where we're at, and it's a closed circle, so that point is good. At 0, we should be at -2, so that's actually your y-intercept, so that's working out. -1, we should be at -3. So looking for the open closed circles and making sure that you are looking at the right function. So yeah, this tells us option A is going to be our graph. So let's say, okay. Select that guy, check our answer. Now, let's talk about domain and range. So this is our graph. What will be the domain for this guy? Now, again, remember, domain is what x values we can use in the function. So how would we define the domain for this function? All real numbers, because even though we're defining in 2 pieces, we are actually still using all the x values because of course that separation is having at x equals 1, right? So all of these values here are basically going from negative infinity to positive 1. We are including positive 1 on this arm, this piece of our function, and then you're basically just jumping and going over here where the 1 is not included. So just imagine if you were to squish those two lines, vertically into each other, the full circle will overlap with the open circle. So you're not really missing out on any x values. You are still using all the x values. So you are still picking up right at positive 1 and then heading towards positive infinity here. So there's no gap as far as the x-axis is concerned. So yes, your domain is going to be all real numbers, negative infinity to positive infinity. All right, so obviously the next one will be, let's talk about the range. So in terms of range, that is the y values, right, that we're getting. So starting down here, you're of course headed to negative infinity. On this side, going up, you're headed to positive infinity. So on the y-axis, what would our range look like? Oh, the intersection. Parentheses on 4. And of course, infinity, negative infinity always take parentheses. All right, so let's say, take a look at this. So kind of think like you're coming from the bottom of the graph. So we are coming from negative infinity, but we have to stop right here because obviously there's no graph for us to continue on. So as you move along the line, of the graph, you're coming from negative infinity. You move along, but you stop right here at negative 1. And since you do have that closed circle, at that point, you want to put the bracket on negative 1, right? Then you are basically making a jump, right? Because there's no graph to carry you all the way up. So you're kind of making a jump till you get over here. And that of course coincides with 4 on the y-axis. But because that's an open circle, you have to put parentheses on the 4. And then of course, as you move along the graph, you're of course headed towards positive infinity. So the y-axis definitely has a gap because obviously we can see physically there is no connection between our two arms of the graph. So you will have to use the intersection symbol. That's what that U shape is, because you are taking two separate sets and putting together. And remember, we had talked about this in section 1.7 when you're using union or intersection to solve your inequalities. That's the same concept you're using here because you have your range in two separate pieces. You have to use that intersection symbol. Sorry, union symbol. I don't know why I keep saying intersection. Intersection is when it's flipped over. You're using the union symbol because you're basically saying I'm taking the bottom half of my y-axis and I'm using it or adding it with the top half. So you use the union symbol. Sergio? How do you know if it's upside down? That's a good question. In domain and range, you're not going to see that being used. But if you were solving like those inequalities that we solved in 1.7, you can see it in those. But again, the examples that we had done, remember the 3-part inequality when we were doing the intersection? So that was where it would actually just come out as a single range of numbers instead of two separate ones. But I would say if you got more detailed into set theory itself, you would see more examples of where the intersection is being used. But as far as like domain and range goes, you're only going to see the unions. Yeah, good question. All right, guys, so let's plug this answer in. Just verify what we have here. So domain was, of course, all real numbers. So negative infinity to positive infinity. And then was negative infinity to negative 1, which is negative. And then parentheses 4. Does that help?
Yeah, no, if the lines were going constant, left and right horizontally, would there really be a simple line? Or would it just be like the top line?
It would have to depend, but yeah, even horizontally, if there's a separation, then in that sense, it could possibly be that your domain is not all real numbers. And the domain could be in multiple pieces. So in that sense, you would again have to use the unions. Alrighty, very good, guys. So let's get back to the last part of our 2.2. So we needed to start with the greatest integer function. These were all piecewise. Let's see. So one thing they're talking about is an application for piecewise functions can be found, you can see in shipping charges. Because obviously, shipping charges are based on, of course, dimensions for your package, but also on the weight of the package, right? So you can see they're talking about how if the weight in pounds for an order is between 0 and 1, and you'll see again, they're using brackets and parentheses on that. So they're basically saying not including 0, because obviously a package is not going to be 0 pounds. It's at least going to be 0 point something, right? So not including 0 and up to 1 pound, right? So they're including the 1 pound. So anything heavier than 1 pound will go into the next category. So anything that's between 0 and 1, including the 1, you may have a certain shipping and handling charges, and you can tell this is an old textbook because it's only $3. Obviously, that's not the current prices anymore, but you kind of get the idea. So when we go to the next level, which would then be not including 1, because we've already included 1 in the first category, so not including 1, but going up to 2 pounds, your shipping and handling charges go up by $1, so it's $4 now. And then, as your weight increases, that shipping and handling charges will go up. So those would be examples of piecewise functions, based on your weight, your shipping and handling charges are going to change. The next example here we're talking about is kind of similar to the shipping and handling example we have here. This one is called the greatest integer function, but this one is defined a little bit differently. So you have the symbol here. You can see we're talking about the greatest integer function, which can be written in this format. So it kind of looks like double brackets almost. I don't know if you guys can make out that there's, 2 lines on that symbol, but it kind of looks like it's got double brackets. Or you can just write it out as integer of x, int of x, so that's the greatest integer function. Now, the way this symbol works, the way it is defined, is that whatever value you have in this symbol, that x is defined to be the largest integer that is less than or equal to x. The largest integer that is less than or equal to x. So think about this. We have 5.01. What is it going to equal? The largest integer, which is less than or equal to that number. So the largest integer less than 5.01 is going to be 5. Now, if you have a whole number like 7, then this is where that equal to concept comes in, because 7 will be equal to 7. But if you have something like 3.2, then the largest integer less than 3.2, of course, is going to be 3. On the negative side, when you're talking about negative 2.2, you're talking about the largest integer less than. It's not going to be negative 2, guys. It's going to be negative 3. Just think on the number line. You have negative 3, and you have negative 2. Negative 2.2 is going to be somewhere here. So negative 3 is going to be less than negative 2.2. So on the negative sides, be a little bit careful when you're defining that. Positives, of course, it's pretty, or I guess a little bit easier to work with than the negatives. But the more you practice, the more comfortable you will get with this. So let's take a look at this. We are talking about, trying to see what the graph for this guy will look like and coming up with its domain and range. Now, when you actually define these numbers. Right, so when you're defining these, now if I use the number 0.5 over here, using that definition of the greatest integer, what should our y value be? The largest integer, which is less than or equal to x. It will be 0, very good. And that is actually going to be true for all the numbers that fall between 0 and 1. But you know the way you're going to write this, you're actually going to put the bracket on 0, parentheses on 1. So it's a little bit different from the shipping and handling charges because you're changing the sides of where you put the bracket. Because anything, think about 0.99999. The largest integer less than or equal to that number would still be 0, right? So anything between 0 and 1 is going to end up becoming 0. In that same way, anything between 1 and 2, and again, you can just use the representative number like 1.5, what will that end up becoming? Yeah, less than. Between 2 and 3, and again, we can use 2.5 as our number. What will that y value be? 2. All right, now let's do negative. So let's see, we did 0 to 1, so that should be negative 1 to 0. And for that, we can use negative 0.5. What will that y value be? Negative 1, yes, very good. Less than or equal to. So this one will go from negative 2 to negative 1. We can use negative 1.5 as our number. Alrighty. I think that gives us good idea of what those numbers should be. Now, here's the interesting part when we try to graph this. So let's take a look at what this graph is. So remember, anything between 0 and 1 is going to be at 0. So on the x-axis between 0 and 1 would be this distance here. And all of it is going to be 0. So I'm actually, I know you can't see, but there should be a closed circle on the left and an open circle on the right. And it's literally just going between 0 and 1. So just that little step. Then we are picking up from 1 to 2. So that's going to be the next, range of numbers. But this one is going at 1. So if you have to do ordered pairs, you can kind of think of, let me pick a different. So you can kind of think of as, 1, 1 can be my starting point, which would be a closed circle. And then 2, 1 would be where that little section ends with an open circle. So you can kind of think of it that way, if that helps. Okay, so 1, 1 will be right here with a closed circle. And then you're going again, this one distance, distance of that one space and an open circle. And this pattern continues throughout. Even though we didn't take all those numbers on our table, this will continue for the entire domain of the x-axis. So closed circle on the left, open circle on the left. And same pattern follows on the negative side. So closed circle on the left, open on the right. You can see it kind of almost makes a staircase. Closed circle on the left, open circle. So I want you to think about this. What do you think the domain for this guy will end up looking? what will the domain for our greatest integer function look? Okay. Yes. All real numbers? Again, think about what happens if we squish all those little steps together. So if we bring them all down and, kind of stack them on top of each other, that open circle is going to go right on top of the closed circle, right? So they're gonna crush into one another, and that's gonna happen for all of these points here. So all those closed circles and open circles are going to get squished together. So honestly, if we compress this, it will end up looking like one single straight line. So as far as the domain goes, you're actually not skipping any values. So yeah, very good. It is going to be all real. Now, what happens? Oh, this is interesting. I'm gonna remove those arrows here, so we can talk about them here. All right, now think about the range. That's the Y values, right? Are we using all the Y values or are we skipping them? Skipping, so how will we write out the domain? Because what Y values are we using? Let's talk about that. What are the Y values that come up when we plug it into this function? Yeah, integers actually, because we're also looking at negatives, right? Whole numbers would only be the positives. So you're only using 0 as the Y value here. You're using 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Same thing here. You're using -1, -2, -3, -4, -5, so on. So you're only using integers as your Y value because everything in between those numbers is being skipped, right? Because of the way the steps in our function work out. So your range is actually going to be set. Well, I don't know if you guys use this symbol here or not, but a lot of times we write the set of integers as an I with 2 vertical sticks on it. If you're not familiar with it, just write it out. Set of integers. But that's how we learned it in India. But yeah, I didn't think that was a commonly used symbol. But now you know. Alrighty, so this is your greatest integer function, which is a piecewise function, but you can see it works a little bit different than the shipping and handling function, so just a slightly different look to it. There's another example that I have included here. This one just shows you, what happens if you add 1 to that greatest integer function, how it's going to change your calculation. So I'm trying to see if I can line this up so I don't have to rewrite everything. Now, if you are adding 1 to your function, how is that going to change our Y values? Same X values, but how does that change our Y value when you do that +1 in our greatest integer? The definition is still the same, the largest integer, which is less than or equal to that value of X inside your symbol, in this case, X plus 1. So if I'm doing 0 as my X value, that will become 0 plus 1, which is of course 1, which is inside our greatest integer symbol. So what will your Y value end up being? 1. Because we added 0 plus 1, right? 0 was our X value. We added 0 plus 1, which made it 1. So by definition, less than or equal to whatever is inside the greatest integer symbol. So in this case, that would be 1. Now you do 0.5. So 0.5 for the X value plus 1 will end up giving us 1.5, which is now in that greatest integer symbol. So same definition, largest number, which will be less than or equal to. Oh, I did something wrong, because this guy should be 0.5. This guy should be 1. So that would be, sorry. This is- If you did 0.5 plus 1. That's 1 which would end up giving us as the y. If we did 1.5 plus 1, that would be 2.5. Okay, now what will 2.5 give us for the y value? That will be 2, because again, it's less than or equal to whatever you have in there. With 2.5, what will you end up with? Yeah, 3.5, which comes out to be a y value of 3. And then on the negative sides, with negative 0.5 for the x value. So you're adding 1, which will end up making it 0.5. So what will that give you as a y value? 0, yeah. Very good. And for negative 1.5. Because it will end up being negative 0.5, which comes out to be negative. So what's basically going to happen is you can see with that adding of 1, our steps actually got moved up 1 level up vertically. So if we try to write this between 0 and 1, we should be on 1. Between 1 and 2, we should be at 2. So basically, between 0 and 1, so that's going to be this distance here between 0 and 1, but we're not on that line anymore, right? We moved up 1. So you can see now this guy has gone up by 1 step. Between 1 and 2, in the previous example, we were here, but again, since you added 1, it moves up that 1 unit vertically. And that's true for all these steps, but you can still see we're still using the entire domain of our function, right? We're using all the x values. The only thing that has happened is our step moved 1 level up, but I'm still using all the x values. So your domain is still going to be negative to positive infinity. And even though we've made that 1 jump, 1 level up, you're still using all the integer values on your y-axis. So the range is also the same as a set of integers. So literally what we've done is taken that original function and just moved it 1 step up. But it does not change your domain. I mean, the graph looks a little different, but domain and range were not affected. And this is something we'll be talking about in next section when we get into transformation, because you will see how, depending on the type of transformation you do, whether it's going to have an effect on your original function. Okay, let's save this guy. And let's see what I see. All right, so here's the last part on this section here. And this is talking about where your function is staying constant, where it's increasing, where it's decreasing. So the idea is you need to be moving along from left to right on your graph. And if you're going left to right on your graph, if you keep moving in that horizontal fashion, right? You don't go up, you don't go down, you just keep moving horizontally. We say you're going constant. But if you're going from left to right and you're making a climb, right? You're going up, that means your function is increasing. If you're moving left to right on your graph, but you're starting to go down, then you are decreasing, because the idea is if your y value stays the same as you move along the graph from left to right, you're at a constant motion. If your y values start increasing as you move along left to right, of course, it's increasing because your y values are getting larger. And that same way, if your y values start getting smaller, you are decreasing. You can see the formal definition over there. They're talking about kind of the same thing I said. If your previous Y value was smaller than the newer one as you're moving along, so if the newer value is larger, your function is increasing. If the older value is larger than the newer Y value, that means you are decreasing. If the Y value stays the same, then you are, moving at a constant speed, or your function is constant, it's not increasing or decreasing. Just to show you some simple examples over here, you just use basic functions to show you, so let's do this. Show you this one. X equals yes. Is this function increasing or decreasing? Increasing, because again, think about this. If you are moving on the graph as you go from left to right, let's get to it. It's not exactly at the mark I'd like it to be, but you can kind of see my Y value goes from 0, 0 to 2, comma 6, something like that, if you keep moving. So again, just as you are moving along, you can see that Y value is increasing, right? Your function is increasing. If we did f of x equals negative 3x, again, you're moving from left to right, so I'm at negative 2, 6, and you can see as we move to the right, my Y values, even my X values are decreasing, but also my Y values. So you can see this is a decreasing function. If you just did f of x equals 3, well, you can see that's that horizontal line. My X values are changing, but that Y value stays the same. So this is where I would say my function is constant. Now, of course, we are showing this to you with 3 separate examples, but you can still see those behaviors within the same graph. They don't have to be 3 separate graphs. So let's take a look at just in terms, what would you say about this function? Is it increasing, decreasing, or staying constant? Increasing. What about this guy? From negative 2 to 1. 1 to 3 to 5. Okay, so what was it doing between negative 2 to 1?
Increase.
Decreasing between 1 to 3.
Increase.
Increasing, and between 3 to 5. So within the same graph, you can see different, and obviously you can see this guy comes from a piecewise function, right? Because no one single graph is going to give you these 3 distinct shapes. All right, let's see how to write these guys down. So this one is asking us to write the domain. So we're doing this for graph A. What is the domain for this one? All your numbers, yeah, very good. This is going from negative infinity. Okay, what will be the range for graph A? Same thing, all real numbers, very good. All right, and of course, we talked about the function is increasing, but on what interval is the function increased times? And the interval notation you use for talking about increasing, decreasing is always going to be based on the domain, the x-axis, not the y. So you're looking always on the x-axis. Where is it? Is it increasing over its entire domain? Zero is just a point, right? We're talking about interval. All real numbers because it is increasing on the entire domain that the function is based on. So yeah, it's going to be the same as your domain. Negative to positive. All right, now we're getting into graph B. The function is not decreasing in graph A, which obviously we see the whole thing as a increasing slope. And it's not constant. All right, domain for graph B. What is the domain for graph? Yeah. Okay, so -2 to what number did you say? 5, very good. Because this is obviously not extending in both directions, right? It's constant, it's staying confined between -2 and 5 on the domain. I know they're gonna ask us for range, so while we have the graph up, let's talk about the range. So that's the y value, obviously. What is your lowest and highest y value?
Bracket.
Let's see, yeah, +1 is the lowest value we have here. And +4 is the highest, and of course, you have a continuous graph, so there's no skipping of numbers or anything like that, so very good, 1 through 4 will be our. Great, so let's begin under. The name is bracket, -2.5, close on bracket. Okay, that all looks good. The range we did from 1 to 4. So bracket 1 to 4, close on bracket. You can see that word out. All right, let's clear this guy out. Now, this is where, as we define, we need to put our increasing, decreasing, and constant at, and we know for this guy, it definitely has all three of those. Now, how will you write your interval notations for all of these? So for the increasing, what will your interval notation look like? On which section of the domain is this graph increasing? 1 to 2? And what kind of symbols will we use on that? Decreasing? Now, when I was learning these increasing, decreasing concepts, I was told we do not use brackets because we're just defining the interval, but your textbook does expect to see brackets or parentheses based on what you're looking at. So we're gonna do what your textbook writes. So the increasing interval is from 1 to 3. That's 1. Check that. Then let's see for the decreasing. -2 to 1. Again, brackets, -2 to 1. And then the last one should be the constant. Instead, we have 3 to 5. With brackets. Okay, questions on this one? Okay, this one will change up a little. They're actually giving you a description and asking you to identify the graph based on the description. If I'm gonna have the whole statement there, I'm gonna have to make it smaller. So as you can see, this guy is saying the bears dominated the market during the first quarter with massive sell-offs. Of course, we're talking about the stock market here. In the second quarter, the market rose. The bears returned to the market in the third quarter and sent the market to record lows. So we're talking about massive sell-offs, the market rising, and then record lows. So based on that description, which graph would satisfy our description? D. So the bears were in the market, we had massive sell-offs. In the second quarter, the market rose, the bears returned in the next quarter, and we had record lows. One answer I got was D. Anybody else have a different? So yeah, you can see we definitely have sell-offs because we're obviously going down in that. Then they talk about the market rising, it did. And we're talking about record lows, which means it's got to fall lower than this lowest point that you had. So this goes down even lower. So yeah, I think B looks like a good option. So this was based on increasing, decreasing, staying constant, but obviously they used a little bit of a different approach on how to apply that. All right, so this is going into section 2.3. This is what I was talking about. We're getting into transformation. So the idea is, how do you take a base function and make changes to it? And how does that affect your base function? Does it change its shape? Does it change its size? Does it cause it to have a reflection and a lot of other things, stretching, shrinking? So first of all, let's talk about what kind of different transformations we can do to a given base function. So the idea here is you have somewhat of a base function, and that can be anything. It can be a straight line, it can be a parabola, it can be a cube, absolute values, square roots, all the different types of functions that exist. So the transformations, this is what the equation for a transformation would look like. So that f of x that you see in there was that original function, but now we have moved it horizontally, we have moved it vertically, and we are stretching it or shrinking it from that a value. So the h causes the function to move horizontally, so either left or right. The k makes your function go up and down. The a value, depending on what the a value is, if it's larger than 1, it will make your graph stretch. If the a value is between 0 and 1, it will make your graph shrink. And if there's a negative on the a value, it will cause a reflection. Okay, and of course, you're going to see all of these in the definitions. So all of the transformations that you do to a parent function will change your, will basically create a new member of your family. So think about, if I just take the basic f of x equals x, right? Y equals x function and make changes on it. Every time I do some kind of transformation on it, it's creating a new member of that family. The transformation changes can be rigid or non-rigid, which means if it changes, if it changes the shape of the graph, it is non-rigid, but if it keeps the original shape, then it's a rigid transformation. So out of your rigid transformations, we are talking about translating and reflecting. So this will not change the shape of your graph. So translating would be moving it horizontally or vertically, and of course, reflection is you're reflecting it on the x-axis. For the non-rigid, which actually changes the shape, that is where that stretching and shrinking comes from. So they will actually change the shape of your function. Okay? So let's start by looking at translations. That's moving it horizontally and vertically. So this one, we're talking about vertical translation. You can see we're talking about moving the graph up or down. So that's coming from that K value. If you have a positive K value, your graph will move upwards. If you have a negative K value, your graph will move downwards. You will see we're putting that K into an absolute value symbol, because if the number is -4, you're moving 4 units down, right? The negative just tells you you're going downward, but you're making 4 units as a count. So that's why they put that in absolute value. So let's look at this guy over here. Again, like I said, we're just using a basic straight line to show you that. So we've got f of x equals x and g of x equals x plus 3. So again, I'm just gonna use Desmos to show you guys how these transformations look. So f of x equals x. Then we have x plus 3. So technically, this is a vertical transformation, which means it should move our graph 3 units up. So if you take a look at this, think about this point here, 0, 0. If we move it 3 units up, that's 1, 2, 3, that changes into 0, 3. And of course, you can use just your mouse to see that. So that's our 0, 0. If I can get it right on the point, you can see that moved it 3 units up. But in this case, what also happens, just because you are dealing with just a basic simple x function, it also moved your graph 3 units to the left. So in this case, this actually acts as both horizontal and vertical, but mainly vertical because that's how the definition works. All right, so that was with your. Let's see what happens if we did it with a square function. But before I get into the square function, can you tell me the domain and range for both of these guys? So this was the f of x equals f function here. This guy was the g of x plus 2 function. Has that changed when we moved our graph 3 units up? No, again, because this is a straight line, it did not affect our domain and range. And again, remember guys, this was the example of a rigid transformation because it did not change the shape of our graph. It just literally picked it up and moved it 3 units up. All right. Now let's do our square function. So that's x squared and x squared minus 3. Minus. So again, if we just use that lowest point 0, 0, you can see that one has been moved 3 units down. So again, it literally just takes your graph and moves it 3 units down. And you can do that with other points. Take a look at this guy here. This one was 2 and 4. When you move it 3 units down, what should that change to? Will it change my x value or my y value? Y. What will it become? Very good. That's going to become this point right over here. Well, if I can get it right on the mark, that you unmark. Same thing happens on the left-hand side, right? So again, this is a rigid transformation because it did not change the shape of our graph. We just moved it. Can you tell me the domain and range? So this will be the domain. and the range for the original function, which is f of x equals x squared. And then for the other one, x squared minus 3, what will be other? So for the original function, what's the domain and range? X squared. For the domain? Did our domain change for the x squared minus 3 function? No. Even though we moved it vertically downwards, it did not affect our x-axis or the domain. What is the range for the original function? That's the one in red. What is the range? Yeah, because your lowest point on the y-axis is 0, you're starting at 0, and of course you're heading upwards to infinity. So did that change for the x squared minus 3 function? Yeah, you moved it 3 units down. Your range will show that change, and you're now starting at -3, but obviously you're still going up to infinity. So in this case, you will see our range does get changed when we do that vertical translation. Questions on this one? Okay. Let's talk about horizontal translation. So again, remember, every time you did a transformation, you created a new member of that family. And that's basically what they're saying. Okay. All right, so we've talked about the k value, which makes your graph move up and down. Now we're talking about the h value. So in this case, what happens is, hey folks, let's do that later. If your h itself is a positive number, your graph will be moving to the right. So from the original, it'll move to the right. Now, if the h value itself is negative, your graph, of course, will be going in the opposite direction, will be going left. But here's the thing you have to be careful about. You cannot look at that sign there to tell you if the h value itself is positive. And here's the reason why. When we define our transformation function, and for that we'll go back up. You can see by default, when we define this, we put a minus in there. Because that's how the transformation equation is given to us. So honestly, when you see x minus something, that means that h value itself is actually a positive number. If it was x plus whatever number, then that actually means the number itself is negative. So you're almost going with the opposite sign. So let me tell you that here. Here. So when you see something like this, which has x minus 3, remember this is coming from that original definition where we already had a negative sign. So this is telling me that h is actually equal to positive 3, which means my graph will be moving to the right. So you have your original function of x squared, which is being moved 3 units to the right. So let's take a look at this, what the graph of this guy will have. So still keeping x squared as our base function, but changing this guy to x minus 3, and then we put the square on the outside. So as you can see here, this the red was our original function. And again, this would be our point 0, 0, and it has moved 3 units to the right. And this point will end up becoming 3, 0. So this time it's your x value that changes. Because anytime you're moving the graph horizontally, it's the x value that will get affected. Same thing over here. You can use this point. And again, you can see this guy would be 2, 4. But when it moves 3 units to the right, it's going to be 4. Because it's the x value that gets added with the 3. Okay, tell me, domain and range over here, guys? Of course, since we just talked about this one, we know this guy is negative infinity to positive infinity, range we know is from 0 to infinity. So for the graph that moved to the right, what will be its domain and range? That's the one in the. Did my domain get affected when the graph moved 3 units to the right? Not really, because you're moving 3 units to the right, but since your original domain was from negative infinity to positive infinity, it honestly does not affect your range, domain. What about the range? Did your range change when your graph moved to the right? No, because it did not move up or down, it moved horizontally, so that did not affect your range. So you can see that, right? With the vertical movement, we had a effect on the range, but moving it horizontally does not mess with the range at all. The range stays the same. All right, perfect. So that was moving our graph to the right. Now, this is where I was telling you, you gotta look at those signs. So you can see this guy is x plus 9. So this technically means your function is, if you put it in that standard format, is x minus -9. So this tells us our h value is actually -9. And that means your graph is moving to the left. So you have to look at the opposite sign when you do these horizontal movements. With the vertical, it shows up in the equation itself, but with the horizontal translation, you go with the opposite sign. All right, so let's take a look at these guys. Let's graph them. So we are going to do square root. So here is going to become square root of x. This will become square root of x plus. All right, so again, for the function f of x equals square root of x, let's talk domain. And this side here is our transformation. Square root of x plus 9. And let's talk about this one. All right, let's start with the original f of x equals square root of x. What is the domain for that function which is in red? And what symbol on 0? Bracket. Yeah, because you are including 0. 0 is included in the function over here. So going from 0 to infinity with a bracket on 0. What can we say about the range for that function? The y values for f of x equals square root of x.
Same as medium.
Bracket. Yeah, because again, on the y-axis, you're headed upwards. As you go right, you're still going up. So you are going to look at 0 to infinity for domain and range. All right, let's see how that change affects when our graph moved to the left by 9 units. What will be the domain and range for the square root of x plus 9 function? Yeah, because you moved your graph left by 9 units, right? So you can see your graph is actually now beginning at -9 on the x-axis. So in this case, your domain does get affected. You're starting at -9 and going to the right to positive infinity. Range? Put somebody else with me. If you all have to do this, something you're going to see. Yes.
When we bracket 0 to infinity.
Yeah, because again, our graph did not move up or down, so the range actually did not get affected. We still stayed at 0 Because obviously, if you look at this, we're still on the same line as this guy, right? So your y value has not changed, it still stays from 0 to infinity included. Oh, very good. So as you guys can see, with each example, it's going to change. It's not going to be a standard, it's not going to stay the same. You will have to look at what your function is, what your parent function was, what kind of transformation you've done to try and see if your domain and range gets affected or not, Now again, remember, these were rigid transformations, so the shape of your graph was not changing. We're doing one more rigid transformation before we get into the non-rigid. So the last one we want to talk about in terms of rigid is reflection. So basically the idea is if you just put a negative in front of your function, it creates that reflection. And this is the idea of where your reflection is actually happening in terms of the x-axis. So they're saying, think if you put a mirror along the x-axis, you will see that, the top half will be reflected at the bottom half. Or if the graph started out at the bottom half of your graph, it will be reflected on the top half. So we're just using something as simple as y equals x. So if we did just x over here, and then create its reflection, negative x. So what's happening in this case is this part of our graph is reflected down here. And this part of our graph is being reflected up. So this half goes down here to the bottom, and this was already on the bottom, which moved to the top. So that's how that reflection is working in terms of this value. So our original function was y equals x, its reflection was y equals negative x. Can you tell me what happens with our domain and range for this guy? When we do the reflection? For domain or range? No, for which one? Both? Alrighty, so domain, of course, is all real numbers, same thing for the range. And even though you did do that reflection, it honestly did not affect your domain and range in that sense, because that whole line is still going to cover all of the x values and all of the y values. So even with the reflection, your domain and range did not change, but that is specific to this guy, remember, because this was a straight line. That's not always going to be true with, all the other functions you look at. So let's look at one more example. This one gives us a nice idea. So square root of x, and then you're just putting a negative in front of it. So square root of x, no, square root of x. So how does that affect domain? Follows the reflection. So let's start with the original f of x equals square root of x, the one in red. We just did this guy, right? So what was our domain and range for this? Yeah, because there's nothing here, right? So you wouldn't have all real numbers. You're starting at 0 and going to infinity. What about the range? Yeah. All right, so how does that, or does that change when we did the reflection? What's the domain for the bottom half, the negative square root of x function? Okay, so the domain did not change, 0 to. You're still going to the right. Still a positive infinity, right? Because on the x-axis, your direction did not change. You're still going to the right-hand side, so you're still at positive. What about the range? Did that guy change, or is it the same as the original function? Okay, so what will it be? With the smaller number. Yeah. So just be careful with that, guys. Negative infinity will now go first. And then it's kind of like, stopping at zero. So it's coming from the bottom and stops at zero. So the range does in fact change because of that reflection. You are at the bottom half of the y-axis, your range will change. So as I was saying, graph to graph, function to function, you are going to see some numbers change and some of them will not. Okay, so this was your reflection. Now again, remember, none of these translations or reflections change the shape of our graph. The shape of our graph has stayed the same. It's just basically been moved around on the coordinate plane. Now they are talking about here is the importance in the order you do the translations or the transformations. So they're saying, okay, what if we started with the x square function, reflected it in the x-axis, and then moved it 1 unit up? The graph, the equation for the graph would then come out to be negative x squared plus 1. But however, if we translated the graph 1 unit upward first and then created a reflection, your equation would come out looking different. So let's take a look at what those two graphs look like. So we have our first equation, which is just the parent function dx squared. Then we are talking about reflecting it first. You can see that's the reflection, and then we move it 1 unit up. So look what that graph is. Now, what if I moved it up first? Move it up first, and then I reflect. Those are not the same graphs, right? Because the order of that transformation was important. So it's kind of like, please excuse my dear Aunt Sally, we do follow an order of how the reflections, translations, shrinking, stretching, and all of that is done. So we'll talk about that as soon as we're done talking about the stretching. All right, so to stretch a graph, you have to multiply your y coordinates with a number larger than 1. So that a value that I was showing you at the beginning needs to be a value larger than. If you want to shrink your graph, your y coordinates have to be multiplied by a number between 0 and 1. So again, your graph will stretch if the a value is larger than 1. Your graph will shrink if the a value is between 0 and 1. And you basically multiply that a value in front of your graph because you're literally multiplying it to your y coordinates. So let's take a look at these guys here. So you can see this guy is a number between 0 and 1. So that means this one should be shrinking. This is a graph. This is a number greater than 1. So that should stretch our graph. So let's take a look at how those transformations will look like. So we're just using the x squared function here again. So let's do the second one, g of x equals 1/4. So remember, this is stretching it, right? So that actually in parabolas, that means it's making it wider. Okay? And you can see this is where the shape of our graph has changed. This is what we call as non-rigid because it's changing the shape of our graph. Now let's do the 4x squared. You can see that makes it narrow. I don't know if this guy hold on. There we go. So the 1/4 in the green is the shrink, or it makes it wider. The 4x squared is the stretch, which makes it narrow. Kind of think about a rubber band, right? What happens when you stretch it, it makes it narrow. So that's kind of what's happening with that 4x squared function. Looking at all three of the graphs, What can you tell me about its domain and range? So we've got the basic function
Function f of x equals x.
squared. We've got the
Shrinking,
and we have the stretch. Let's start with the first one. What is for the basic parabola, f of x equals x squared, what's our domain and range? For the domain?
Yeah.
What about the range?
The range is gonna be bracket 0 at the, infinity.
Okay, so has that changed for the g or the h functions? When you did the stretching or the shrinking? No, because we have not moved the graph, which in the parabola review wouldn't matter even if you moved it horizontally. Vertically is where you saw the range changes, but in this case, they're all at the same place. They're just wider or narrower. So this is actually going to be the domain and range for all three functions. So that actually did not change in this case. Questions on this one, guys? Right. So basically, they're talking about when you are shrinking, or for that matter, stretching, your ordered pairs will change because it's directly affecting your Y value. So keep that in mind. It's those, all the Y values basically get multiplied by whatever that number was that was being multiplied. So since we did 1/4 x squared, in your original table for the x squared, all the Y values now got multiplied by 1/4. When you did the 4x squared, all the Y values got multiplied by 4. So if you had done these tables over here. So, you know, again, if you use just the standard 5 numbers that we normally do. And this would be the x square function, this would be the 1/4 x squared, and this guy would be the 4x. Let's see, what is this guy come out to be? 4, 1, 0, 1, and 4. So now think about this. If you took the 4 and multiplied it by the 1/4, what would you end up with? 1. If you took the 1 and multiplied by 1/4, can't be that hard. 1/4. 0 times 1/4 again is 0. So this guy would be 1/4, this guy would be 1. So all those Y values basically got multiplied by a quarter. This one over here, you would be taking your Y values and multiplying it by 4. So this would end up becoming 16. 1 times 4 would of course be 4. 0 times 4 would be 0. So it's whatever you have as the original Y values, they are the ones getting multiplied by 1/4 of it.
In the second box, shouldn't the -2 and 2 be 4? Negative.
What do you mean?
So you wrote down -2, 1, in the second box.
This one?
Yeah. Should it be -4?
No, because you are squaring your X values, you're not gonna have a negative sign left over, right? If you're taking X squared,
But shouldn't we do it by negative?
I'm keeping my X values the same in all 3 of my graphs. Right? Because are you changing those? Okay, so I'm a little lost then. So if I'm using -2 for my X, what will it be then if I did for -1/4 times -2, you know, just going by that definition? -2 squared would give us +4. +4 times 1/4. Give you 1, right?
Let's just give this.
Okay, all right. So like I said, if you have your original function, your original table, you're literally just multiplying whatever that A value is to your Y values, your X values essentially are staying the same, and it's just the Y value that changes. Alrighty, let's clear this guy out. This is the order you need to follow when you're working with multiple transformations. You will always move the graph horizontally first, so that's the H value, so the graph moves left or right first. Then we do the reflection, shrinking or stretching, which comes from that A value. And then the very last thing we do is the vertical translation, which is the K value. So the order is we do horizontal movement first, then reflection, stretching. Obviously, both stretching and shrinking are not going to happen at the same time. So you may have a reflection and then either stretch or shrink. And then the last thing you do is that vertical translation. So you need to follow this order so that everybody will then be looking at the right graph. Okay, so there will be no confusion. So let's take a look at this example here because it's having us do it step by step. Let's write it down so I can translate it. So we have -1/2. So you can see there's a reflection, there's a shrink that's happening, square root of x plus 2. So that's the horizontal movement. And then you have the +4 on the outside, which is your vertical movement. What's our base function here, guys? What is the parent function in this example? Y equals -1/2 square root of x plus 2 plus 4. We talked about x squared as the parent function. We talked about just y equals x as the parent function. Square root of x, very good. Your parent function here is just square root of x. All right, so remember, we do the horizontal movement first. So the horizontal movement is going to come from which one of these numbers? The 4 or the 2? Which one is it? It's going to be the 2. It's the number that's been added or subtracted from the x value itself. So since we have square root of x plus 2, is our graph moving to the right or the left? The left, because you go with the opposite sign. So it's going to be square root of x plus 2, and you should see as soon as I put the 2, my graph is going to move 2 units to the left. Okay, so the graph moved left. So we start by the horizontal, then we do the reflection, stretching, shrinking. So y equals, and I'm actually going to do the reflection first, so square root of x plus 2, you should see we have our reflection. So at this point, we're still working on rigid transformations, right? It's not changing the shape of our graph. It just moved it to the left, and now it's done a reflection. Then we need to do our, in this case, would be the shrinking. And let's save some time and maybe copy paste. And then let's put in our A value, so that's the 1/2. So this is where the shrinking happened, and it has changed the shape of our graph. So you can see the red one was a little bit more wider, and this guy has become a little bit narrower. So in this case, that's the shrinking that has happened. And then the very last thing we do is the vertical transformation, which is where we're now going to be doing that +4 at the end, and you should see that takes our graph and moves it 4 units up. Let's. So let's start with the original function
What is the domain and range?
for the original square root of x function. 0 to infinity, right? That's this guy. Start at 0, you're headed to infinity, same thing on the domain and range, 0 to infinity. When you did the translation to the left by 2 units, what did that change? Domain or range? Or both? Domain, what was our new domain? -2 to positive infinity, did it affect our range? No, because our graph did not move up or down, it stayed where it was, so the range at this point is still the same. Okay, when we did the reflection, which is the graph in the red, what changed, domain or range, or both? What changed with the reflection? Both, so what's our new domain?
-2.
So actually, it did not change our domain. And we're going step by step, right? So from the original, it has changed, but not from the moving to the left. What's the range? Is it the same or did that change? Okay, what's the new range?
0 to negative.
Again, put the smaller number first, so negative infinity to 0. Yeah, because you have reflected it on the negative side of the y-axis, your domain, your range is again going to change, right? It's going to show that we have a reflection. All right, when you did the shrinking, how did that affect our domain and range? With the 1/2. Did it change my domain? No, because our starting point is still at -2, and we're still headed to infinity. Did the shrinking change our range? Yes, no, maybe, I don't know. No, because you're still coming from negative infinity here and you're still headed to 0. So negative infinity to 0, including 0. Okay, and then for the very final function itself, domain and range, what changed? Because this time we moved it 4 units up, so did that affect our domain and or range? What's the domain? And that's the function in green at the top. What's the new domain and range? Or
I think it's the
domain or range, which one are you talking? Domain? The why negative infinity? Because you're still talking x-axis, right? So domain for that final function. Yeah, so yeah, we did move the graph 4 units up, but again, it's still in line with -2, right? So that position has not changed, which means you're still going from -2 to the right-hand side, which is taking you to positive infinity. What about the range? Now remember, your last range was negative infinity to 0. Is that the same or has that changed? It's okay if it's the wrong answer, that's how we learn.
change from negative to negative.
Perfect, because we didn't move our graph 4 units up, that is going to affect your range. So yeah, we're still coming from negative infinity because obviously this part of our graph is still headed down. But now instead of being at 0, you moved 4 units up. So your range also moves 4 units up. So you are going to have a new range. So in most of these, you can see when we move the graph to the left, it changed our domain. When we did the reflection, it changed our range. And then when you did the vertical translation, it changed your range again. You didn't put that away. I shouldn't have to tell you that in every class. So depending on the transformation, it can affect your domain and range. So just be careful of that, okay? And I think this example shows you very nicely as you go through those multiple translations, look at how different our final graph looks from where we started out at. So let me just save this guy real quick and I'll get rid of all these intermediary functions. Let's get rid of this writing, and you can see where our first function started at and where you ended up at. And we have now moved it to the left. We've reflected it, we've shrunk it, And then, of course, we moved it 4 units up, and it does change. You can see there's a slight change in the shape because it's not as wide as the original function started. And then instead of being at 0, 0, you're now starting at -2 and 4 on, the point where the graph begins at. All right, questions on this one here? Okay, so this was to show you how the multiple translations work out. Again, guys, as I was talking about how each time you do a little transformation, it creates a new member of the family. So they're actually talking about the basic identity function here, the y equals x. And it's called the identity function because your x and y values are always the same because it's y equals x as the function. So if x is 1, y is x is -3, y is -3. So basically this is a graph that crosses the origin of our coordinate plane and it will have a slope of 1. So anytime we make any kind of transformation on this, it's going to create a new member of its family. But basically, instead of using that transformation equation here, we can actually just write it in the simple slope-intercept form as mx plus b. And so what they're doing over here is just showing you how, if you started out with this transformation format, you can distribute that a inside your parentheses, which ends up giving us ax minus ah. And then of course you have that plus k at the end. And the negative ah plus k is basically two numbers being added or subtracted together because x is the variable. H, A, K are all real numbers. So you multiply A times H, there's a negative on that, plus K, whatever those two numbers come out to be, they end up becoming our y-intercept value. And of course, AX is the same as MX. The A becomes your slope. And you can basically end up in a slope-intercept form of your equation. So again, we're kind of tying back to where we basically started this class at, is you're basically looking at a linear equation with a positive, negative slope and a y-intercept. You can even have a zero slope depending on the kind of function. So they're talking about, what this sort of a transformation might look like. So our function is y equals -2x plus 5. So you would be starting out with the parent function y equals x. And then we would be doing, let's see, horizontal movement first. So if we look at -2x plus 5, there's technically no horizontal movement. So we can start with the reflection. Then we can do the stretching. And you can see in this case, the stretching actually looks like a steeper slope. So you're not going to see the wider or the narrower effect, but the slope will get steeper. And then the final thing is our vertical movement, which was the plus 5. And you can see that's what our final graph will end up looking like, is the function in B. And again, look at from the black line where we started out at, which was the identity function. We have now created a reflection. Then we increased its slope, or basically stretched it, and then we moved it 5 units up. So again, if I get rid of these intermediary steps, you can see where we started and how we ended. But at the end of the day, you're still looking like at a linear equation, right? A straight line with the slope of -2 and a y-intercept of 5. So that's kind of what they're talking about there. All right, before we get into the symmetry part of things, any questions on these transformations? So you looked at moving it horizontally, vertically, reflection, stretching, and shrinking. Anything? And we will be revisiting this idea of transformations as we get into other functions as we move forward. So with exponential functions, logarithmic functions, and something else I'm missing, but I know we're going to do a bunch of polynomials, but we'll be revisiting this concept. So just make sure you're clearing your questions now. One second.
Is the reflection always on the x-axis?
Yes, in this sense, the reflection is always on the x-axis. Yeah.
We would be doing the cube. Perhaps.
They may show up in the functions, yes, because we will be doing higher degree polynomials. So yeah. Any other questions on the transformations? Okay. So symmetry is not a transformation. Symmetry, as the name suggests, we are literally talking about two halves of our graphs being equal, identical, similar. Now there can be different types of symmetry we'll be talking about. So here you can see if we reflect the graph f of x equals x squared in the x-axis, that's the reflection that we talked about. It gives us the function g of x equals negative x squared. So basically the idea is if we were to fold the graph along the x-axis, so fold your graph along the x-axis, you can see those points 2 and 4, 2 and negative 4, or the point -2, -4, and -2, +4 would basically end up coinciding, right? We can also talk about this distance here between the x-axis and the point on the upper graph and x-axis and the point on the lower graph. These will be the same distances also. But at the same time, this is technically not symmetry. This is reflection. When we talk about symmetry, we're actually talking about on the right-hand side. So parabola has its own symmetry. Now you can see this is a parabola where the vertex of the parabola, which is that lowest point of the graph, is at 0, 0. So when we talk about between the left and right hand side, this distance here between the y-axis and the point 1, 1, and the y-axis and the point -1, 1, that's going to be equal distant, or as we say, equal distant. Same thing here, this distance here and this distance here is going to be the same. So the same idea, if we fold our graph along the y-axis, the two halves will be exactly identical. And that distance, as I said, between the points will be the same. And that's going to be true throughout the length of your parabola as it's opening upwards. That is what we talk about symmetry. So we say this graph f of x equals x squared is symmetric about the y-axis. But you can also have symmetry in terms of the origin. Now, any even function, so that would be something like y equals x squared, because your exponent is 2, any even function is going to have symmetry about the y-axis. So x to the 4th, x to the 6th, x to the 8th, x to the 10th, any of these functions that have an even exponent are going to be considered as even functions, and they will all have symmetry about the y-axis. So let's take a look. It does. So of course, y equals x squared. How about y equals x? And you can't see it, but there should be a little bit of that slight hill happening in the center there, but it doesn't show. Okay, what if we did to the 6th power? You can see all of these are going to be even functions with symmetry about the y-axis. Now, if we talk about odd functions like your f of x equals x to the 3rd, now you won't be able to do the whole folding thing that we can do with even functions, but with odd functions, we talk about symmetry with respect to the origin. So that actually means if you look at the distance from the origin to, one of the points on the graph and do the same thing on the opposite side, that distance is going to be the same. So with origin, it may be a little bit hard to visualize because, like I said, you cannot do the whole folding thing, but we're talking about in terms of distances. So the idea is the distance from 0, 0 to this point 2, 8 is going to be the same as the distance from 0, 0 to the point -2, negative. Same equal distance between the two points. And that's going to be true for all odd functions. So again, just to show you very quickly, this is our x to the 3rd function. Let's do x to the 5th. You can see it again kind of follows the same pattern. We'll do one more, x to the 7th. All of these are examples of odd functions which are symmetric about the origin. And honestly, guys, the best way to remember is O goes with O. So odd with origin. So all odd functions have symmetry about the origin, which automatically means then even functions will be symmetric about the y-axis. So O goes with O. That's the easiest way to remember odd with the origin. Now, obviously, not all functions we're gonna get are going to be just one, a monomial with just one x value and one exponent. So we will need to look at some tricks and techniques to identify if a function is odd or even. They're giving you a little bit of a hint over here. So they're saying if you have an odd power of a negative number, so I'm looking at this little guy here. So we're saying if you have an odd power of a negative number, then your answer is going to be negative. If you have an even power of a negative number, your answer is going to be positive. So the idea is if you have a negative base with an odd number, you will end up getting a negative answer. If you have a negative number with an even exponent, your answer will come out to be positive. And we know that's true. Think about -2 to the 4th power and -2 to the 3rd power. This is going to give you a positive answer. This is going to give you the negative answer. What is 2 to the 4th power? 2 to the 4th power? 16. And 2 to the 3rd power? 2 times 2 times 2. Okay. So it's basically what is the exponent? Is it an odd number or is it an even number? Will tell you if you're going to end up with a positive answer or negative answer. And this is going to come in handy when we start looking at examples like this one, because we will need to figure out, are we looking at an odd function? Are we looking at an even function? And based on that, what kind of symmetry is our graph going to have? Because the next thing that we're building up to is how do you graph higher degree polynomials? And there will be some characteristics that we will be looking out for. So symmetry is going to be one of those. Now, of course, the idea is we do have access to technology, so we don't have to do a lot of these graphs by hand. But part of the course is to recognize some of those characteristics of these graphs so that the graph you're looking at is the right graph, because it can take one little typo and the graph that your computer or Desmos or something like that is spitting out may not be the accurate graphs. If you can recognize some of these characteristics, then you have the right graph. All right, guys, so this is where we'll pick up from. We just have to talk a little bit about these symmetries, and then we'll talk about inequalities. So we'll be done with 2.3. We do have 2.4 and 2.5 to talk about. Obviously, we're not doing these on Thursday. We'll probably move it to Tuesday, well, basically a week from today. Okay? Those of you who have not started on your homework, this is a good place to start. We're at 2.3 now. You have 2.5 sections of homework to do. Let's not fall behind, okay?
Yes.
Is that the next one?
Like 4,
Yeah. Again, you guys can create your own note card, base left on the old one, which I doubt if they would have had. You can use that or. Hold on, I did not stop recording that. All right, what was the question?